We are back with our friends from Fresno State Physics Outreach. So joining us now is Professor Don Williams. You recognize him from all the crazy experiments that we do today. And today we're talking about linear momentum. And you're going to explain what that means. So anybody who hasn't caught one of your segments today, you're explaining science.
Exactly.
This is what you do all around the valley for kids so you can teach your students how to teach science.
Nailed it, Emily.
Teach me linear momentum.
I am, and linear momentum is basically mass times velocity, right?
Okay.
So right now I have no linear momentum, right? But then when you start moving, you do, huh?
Okay, now I do have linear momentum.
Now linear would mean in a line, though, right? You have to go in a line, not in a circle, right? Too. Now you understand velocity. That's pretty easy to understand, right?
Sure.
Fast and slow. But what about mass? What about
I have a lot of mass.
Do you really understand what a kilogram is? Like if I take that to the moon, is that still a kilogram?
Yes.
Say yes.
Okay, yes.
Yes. Would it weigh differently
it
on the
will weigh different because of the gravity's pull.
Exactly.
But it is still a kilogram.
It's still a kilogram.
Okay.
You can think of it as all the atoms in there, right? So no matter where I took that, would it still be a kilogram?
Yes.
It would be, exactly. Now, on Earth, we can weigh it.
Okay.
And the audience can see. We don't use pounds. That's newtons.
Okay.
10 newtons. So 1 kilogram on our planet weighs 10 newtons.
All right.
Okay? That's the same as a liter of water. Weighs 10 newtons. So that's a kilogram of mass too.
Okay.
All right? Now, we're going to step out front and we've got 2 scales where we can weigh you on the Earth and on the moon.
Okay.
On the moon, which you're going to weigh less.
Okay.
In newtons.
Okay, so similar to what we were talking about.
Exactly. So the first one, you're going to get on this one first.
I'm comfortable with myself.
I know. Wait, you got to get on the Earth first. Wait. That's going to be on the Earth now.
This is the Earth.
Okay, she's on the Earth.
I had a big lunch today, folks.
You did, and she weighs about 730 newtons. Now, don't forget, that's newtons.
I'm a very dense person. Okay.
All right, now, how many newtons does she weigh in the moon? Only 120. There you go. Only 120 newtons.
You're trying to make me feel bad about myself.
Are you still the same mass, though, Emily?
Yes.
Yes, exactly.
From here to here, yeah.
You're still the same mass. So that's the big difference. All right, let's go around back now. Now, one of the real special things about linear momentum is when something has linear momentum and it makes a collision, linear momentum is conserved, or it stays in there.
Okay.
Right? So we can take a couple of our little cars here. Remember how we're the Bulldogs, we're the blue and the red, right? And I'm going to have that one be sitting there, and watch what happens when I bring this one in and collides with it.
That one stays there.
Exactly, and that one takes off. Now, you notice they're the same mass, so whatever speed that goes in, it takes off with the same speed, doesn't it?
So linear momentum is
mass times velocity.
Conserved or transferred?
Both. Conserved means it stays in there.
Okay.
It stays in there, exactly. Now, what do you think's going to happen if I take and I put a bunch of mass in the car that's going to sit there?
Okay.
And I'm going to push this one that's lighter into it. What do you think is going to happen?
I think
Is this going to fly off the same speed now?
Not the same speed, but it will fly.
A little bit, and the other one might go backwards.
Oh!
Yeah. Now, what if I do it the opposite way, Emily? What do you expect to happen? Now I'm going to take the
opposite reaction.
Exactly. It's going to knock the heck out of that thing. You ready? Here we go. See how fast that one took off?
Yes, and then that one still
had a little bit of momentum.
Okay.
You can see the idea. So if I put more and more and more in here, you can see how it would still be transferred no matter what. Now, it's also transferred in explosions.
Okay.
When you start with something that has no linear momentum, it still has to have no linear momentum when it explodes.
Yes.
So whatever's carrying it off this way carries it off that way.
Okay.
So we're going to show it.
Show me.
I am, with a one-dimensional explosion.
All right.
So I've got that little piston in there. I'll put the 2 cars together, and I'm going to tap that button, and it's going to explode. Here we go.
Oh, I see.
Boom. And they careen off at the same speed.
At the same speed.
Because they're the same mass. So what are we going to do next, Emily? We're going to add some mass to one of them. You tell me which one, this one or this one?
Do the red one.
Do the red one, okay? So let's add a couple of pieces of mass to the red one. Now I'm going to explode it. What do you expect to happen this time?
This one is not going to go as fast.
Beautiful.
Okay.
You got it. You got it. Here we go. just like you said.
There,
huh?
ah!
Whoa, there goes our car over the edge,
Over
too.
over the cliff.
That's all right. We'll get that a little bit later. So you can see linear momentum, no matter what, is conserved in collisions
Yes.
or explosions.
And so in physics, we would use math and physics to understand the rate at which things
Absolutely.
explode, the rate at which things crash, the rate at which energy is transferred.
Exactly.
But I can understand the concept. I don't know if I can actually do the math.
You're exactly right.
That's what you're teaching. So you're going to stay here. You actually brought along one of your former students.
I did, and he's actually going to carry this a little further.
We're going to see how well your teaching did. So everybody stay right there because we have more from Fresno State Physics Outreach when we come back.